Okay, so next speaker is Professor Vinjanampathy from IIT Bombay, and he is going to talk about what? Interferometers?
Basics of quantum metrology.
Okay, so Sai.
Okay, thank you very much, Subhadeep. Thank you to the organizers to begin with. This is a tremendous opportunity. I feel very privileged. I'm also extremely lucky to be with many friends, old and new, and so let me take it away with that. So I just want to say that what's the saying? Dress for the job that you want, not the one that you have. So I'm essentially giving the lecture that that I have been petitioning for many years now. Anil and many people from the Quest circuit know this, which is essentially to do something like a SERC school around various aspects of the pillars of NMQTA. So I apologize to the experts. I'm going to bore you to death. Please feel free to correct me if I'm making mistakes. What I'll do is basically essentially just do maybe 3 board lectures. Yeah. So and so feel free to interrupt me and not to finish anything that I've started. The important thing here is just for me to basically hopefully walk you through some of this stuff. Okay, so those are the kind of warnings and apologies. So let me just tell you what the plan is. The plan is I've presumed something very severe, which is that you don't know anything about quantum metrology, right? And so again, there are various levels of expertise in this room, but I presume that it's good for all of us to just go through some of the stuff. If you're a first-time learner, then it's great. What I will do is not have enough time to basically solve everything, but I will tell you what to do to solve things, and then we can use the Thursday afternoon lecture to actually sort out. So I also have a series of problems that I'll basically propose, homeworks I call them because of old habits, that I'll propose today and tomorrow, and then we can discuss them offline, but also just do them. Okay, so with that, let me just say that, so what I want to begin with before I, well, okay, maybe let me start with references. So nothing I'm going to say is original. So I want you to know that on the ground floor. So there is a very famous book by Stephen Kay. It's Fundamentals of Statistical Signal Processing. You don't have to write any of this down. All of these notes, after I've error corrected them, I'll put them so that ICTS can just link them to the video lectures that will be available, so you can just download the whole thing. Yeah. So what I want to share with you are the resources and what somebody who's coming into this field would do. So there is a book by Stephen Kay. It's a very famous one, Fundamentals of Statistical Signal Processing. And if you don't, if you've never done any of this stuff before, estimation theory, so on and so forth, that's a great place to start. It's a very well-written book. And so I'll hint to you some of the things that are in the beginning chapters of that book. This is the classical stuff. In the quantum, I want to point at 3 references. One is a review by Matteo Paris. I'll just write the reference here. It's the archive reference. There is Reviews of Modern Physics by Petsy et al. It's a long list of folks here. And this is RMP 90 03505, and you should get this. And last but not the least, there is actually, I think, an excellent review, which I recommend to my group all the time. I've read it several times. So the lectures for the next 2-3 days are basically collections of this stuff and some other stuff that the organizers and I have spoken about, but I'm leaving it a mystery so that I can adjust according to what happens today, what happens on other days. Okay, so these are the references. There are several more. There are books on measurement theory, if that's something that's new to you. There are books on continuous measurements. There are books on a variety of different things that are noted here. So I'll leave that for you to sort out later. Okay. So with that, let me I just want to say a couple of words about kind of folklore, intuition, and what I expect the takeaways from these series of conversations are. And so the folklore is something very simple, which is I have some parameter, and let's presume for a second, let's ignore for a second whether I want to know this parameter or I'm allowed to vary this parameter. And something happens, and I'm measuring some quantity. And so if you've seen classical versus quantum metrology, all of the conversations about making these peaks more in number in a given interval, right? So it's the cosine phi versus cosine n phi in Carl's talk today morning, right? And so this is a kind of intuition. It's a very good intuition. But there are catches to this that I want to basically just point out. The catches are well known to the field. So this is point number one. Point number two is, maybe you've come across a formula like this. Right? And there are caveats to this as well. This is only valid for unimodal distributions. Right? It has to be the simplest object where this thing essentially works. And point number three, right? This question actually is the first question, which is what peak are you on? Right? So I'm asking you a series of questions. I apologize because I first want you to first be interested in the question, right? Once you're interested in the question, the answers can be sorted out more or less. But if you are a little bit confused, like I was for many years, as to what the question is, this is my attempt at trying to sort it out for you. And so, these are the kinds of things that we'll ask, right? We'll ask, is this formula good enough, right? When does this formula apply? When does it not apply? When should I basically worry myself with these Fisher information formulas as opposed to something like this? My friend in the lab is using this. I'm using something else, right? What peaks are you on? This is a question of global versus local metrology, right? And so can I tell, do I have to tell which peak I'm on and where on the peak I am, right? Or can I just basically just locally track basically variation of the measured signal, right? This is a question that you can ask. All of these basically relate to the basics of metrology, classical and quantum. And the final takeaway, hopefully, partially at least, is to basically relate experimental data with measurement models. Right? And so if I can relate experimental data to measurement models or make a conversation about this, then I think we're on our way, right? Okay, so that's what I want to say. I probably will barely scratch the surface of this, so I apologize for the slightly grand entrance here. Okay, so with that, how is this question posed, right? How do you take something that's very specific in an experimental context like this and generalize it to a context that can be discussed so that it can then be applied to all experiments, right? All of them all at once. And so this is the question of parameter estimation. Right, and so the question of parameter estimation is that I have some sort of time series, you can think of it. I've been warned not to write close to that wall. So I'll draw myself a less than straight line to ask myself to keep below that. Okay. So I have a time series, and I want to invert this and find some parameter phi, because I know that the time series depends on the parameter phi, right? So more formal definition was provided earlier, but this is, in simple, my simple interpretation of it. Okay, so we interpret this as the experimental data. Right, and so of course it's usually full of noise, right? It's replete with noise. And this is the parameter we seek to find, and it belongs in some set. So 0 to 2 pi usually, you just normalize it and then set it to 0 to 2 pi, 0 to 1. And so that's the question, right? So you can ask this question in many, many contexts. And this is, again, on the ground floor, I want to express. So there are two contexts here that I don't consider. Context A is multi-parameter. This is straightforward to do. Once we've done the single parameter, the multi-parameter simply amounts to putting things as vectors and then thinking about the vector quantity and hence covariances and so on and so forth. So in principle, straightforward to do. And if you're interested in this, I point you to any of these reference reviews. I remember reading it from SK19 most recently. The second is, I will always be in the IID regime, right? And what that means is I'll assume that I'm making enough statistics that I can essentially just talk about asymptotic quantities. So if you are worried about what that phrase means, then Stephen K is a good reference. But there are technical references which actually solve this problem. I'm just going to put names here. The entire point of this is so that you know what that name means, so that you can look it up like 2 years from now when you need it. Okay, so one of them goes by the name Ziv Zakai, and there is a reference. I know an incomplete reference, I apologize. Which is this paper by Manke Sang, who's now at NUS. So if you are interested in that, you develop an interest in that, you're an advanced student or listener, then that's where I direct you to. Okay, so with that, I think I've finished all of the caveats, right? I've narrowed the problem down enough that I can now talk about it. So mathematically, what I have is, I have a set of measurements, let's say M1, M2, so on and so forth, right? N sub n, given theta. And so what I presume is that this is coming from a probability distribution, right? So all that it means is they can be independent events, right, that have nothing to do with each other. And you're just drawing from some distribution that is generating these events, right? So if my beam splitter transmission coefficient is this much, then that's an example of the kind of data that I will see. And asymptotically, I can make comments about what that data looks like, right? Okay. And so this, for brevity, I'll just call the vector of measurement M, and M is a random vector, right? And it's realized from the set of measurements, which I will refer to as capital M, right? And so why am I doing it like this, right? What I want to do is to be able to talk about two things, basically one after another or right next to each other. One is I've taken 50 measurements, And at the end of 50 measurements, I want you to tell me what the transmission coefficient for the beam splitter is, as well as you can, right? And the second is, I take as many measurements as I want, and I want you to tell me how well I could have done, given the kind of resources that are available, right? So both of those are relevant questions. They're relevant for different reasons. One is kind of the, what can I do with what I have? And the other is, what's the best I can do, right? Questions which are at different ends of the spectrum, yes.
So this random vector is sampled for this from this probability distribution, or
Yeah.
Is it okay?
So the whole point is that it's a parameterized probability distribution, and you don't know the parameter, right? Yeah. So you imagine, right? So you imagine that when you switch on your Geiger counter and it's going click, right? It's a bunch of clicks that you're registering, that you're sampling from some distribution. Is the unknown parameter, sorry, did I shift from phi to theta? I tend to do that all the time because I'm in the limit that theta equals phi. Yeah. Okay. Okay, so here at this point, I declare, with apologies, homework 1, which is consider a biased coin 2/3, 1/3, and a finite number of measurements n, right? And ask yourself what you can make, what comments you can make about this. Let's say you take 100 measurements, what can you say, right? So it throws more surprises than you'd believe. So I leave it because we can discuss this offline, but okay. So what I just said was basically that P of small m comma theta comma phi capital M comma is a probability distribution function from which small m is drawn, right? And the task is to basically try and invert this, right? And at this point, I make my first strange sounding question. So my strange sounding question to you is the following. I give you a stick and I ask you to find its length, right? It's about that big. What do you do? You get a ruler, point it at it, right? And then I say, I don't believe the ruler, right? So what I'm trying to draw your attention to is that every act of measurement is essentially a map between something that you believe and something that you measured, right? So you want to make this map. And the map is only as good as basically all the underlying assumptions that sit on which this thing sits, right? So from that context, what I want to introduce you to is this notion of what is called an estimator. Right? So I've done two things here. One is I've written phi with an inverted hat on top. This is the notation that Koch, the review by Peter Koch takes. And I will use this because hats are used as quantum operators, right, in quantum mechanics. So this avoids that confusion. But if you look in Stephen K, for instance, hats are estimators for him. So usually the statistics folks who are older than us, in lineage, they use hats, but we've already reserved hats to do something else with it, right? So this inverted hat you will excuse. So what this estimator is it takes you from one finite set of measurements, right? It's a map between the finite set of measurements to basically this phi min, phi max. So what it does is it's a way for you to rationally invert the problem that you've been given, right? The problem that you've been given is I have some data and I need you to tell me what the beam splitter transmission coefficient, for instance. right, in this imaginary example in my head, right? And that act has to be done rationally, right? Which is to say that we have to put down some rules for what this map can be. But first I introduce to you that this object exists. And then I tell you that this object is how you've been measuring everything in your life, right? So the moment I challenge that ruler, then you have to go bring something else that you trust a little bit more, so on and so forth, right? And to establish trust on fundamental rulers, right? That's many of the experts in the audience today, yeah? Okay, so this, so this object, this estimator, is also a random variable, right? And it has several properties which two key properties that I want to talk about right now. One of them is that it's a random variable. And the second is that it depends nothing on nothing except the data that you provided, right? Because if it depended on something that you didn't measure, that wasn't a measurement record, how could you put it in rationally, right? It can depend on parameters of the problem, but it has to depend on nothing more than, once the machine is ready, the function is ready, it should be fed with nothing more than the data, right? So here again, I'm just essentially copying for you some problems from K. So oh, sorry, let me just draw this line. Right? The IID drawn from right? So let me just talk you through what I've just written on the wall. So let me say that I have a Gaussian distribution. That's what this thing says, N, normal distribution, mean mu, and standard deviation sigma square, right? Variance sigma square. And now what I say to you is that I know the variance, but I don't know the mean. And now I want you to come up with, talk about, go look up, right? What an estimator for this would look like, right? Let me venture a hint that if you, yeah, go ahead.
We are primarily assuming that this phi that we are going to estimate, that the set of MA values depends on phi.
Yes.
But now if we take this estimator as a random variable, then we are saying the reverse map is not depending on.
You're just conceding that this is a random variable because the measurements are considered to be random variables. That's all.
I see.
Yeah. Okay. So no, there's nothing crazy. If you look carefully in any of these books, Stephen, for instance, there are these. I forget what they're called. Nuisance parameters, nuisance measurements, I think is what they're called. You could perform a measurement where you're trying to estimate some parameter, and then there's a bunch of stuff that doesn't depend on that parameter. This happens, and there is a way to deal with it. It makes measurements worse, usually, right? So if you just follow that line of thought, there is stuff there. But let me just, yeah. Okay.
I have one question.
Yes.
So these measurements are also bounded, just like phi minimum, phi maximum?
No, it's some map between whatever model that you have. So let me just say in simple English, right? So what I'm doing is I have a little laser pointer here, and I point it at the wall, right? So now my angle of deviation, right, is the parameter I'm trying to estimate, and what you're measuring is on the wall. Depending on how far I push it, right, that can be anything. right? But there has to be some rational model that takes me from this object to that object, that's all, right? Okay. So yeah, so I was going to give you a hint that try and take the mean of this, right? And then try and work out if that works. Try and take the mean of the finite size sample that is given to you, yeah? Okay. So with this, let me make a point, which is that a good estimator, yeah, and sorry, please point it out to me if you can't read something on the wall. A good estimator should have the following property, which I'll write down what it is, and then you can see what we can see what it means. I would like for it to have the property, this property. I'm happy to settle for this property, right? So sorry, I've again reverted to theta because somehow I made my notes with theta and I started with phi. Yeah. So let me say what this means in words. What I want my estimator to do is if the actual deviation, right, is like 1 arc second, I don't want my estimate, it would be fantastic if at the end of 5 measurements, I compute the estimator and it just says 5 arc seconds, not 1 arc second, whatever the number I just said was, right? 1 arc second, right? But this is too much to expect because typically you have noisy measurements and this is never going to be the case, right? So this would be super nice, right? And definitely impractical. Is this clear? What I'm asking here? I'm asking, I've made 5 measurements, right? And I compute, you're in high school again, right? Please compute the acceleration due to gravity near Earth's surface. You take 8 measurements and you compute basically whatever it is you compute, it spits out 9.8 to 10 decimal places. No need for advanced gravimetry, right? Not the case, right? This is not the case, definitely not the case. What you would like for it at least to be true is that if you take enough measurements, that basically there's nothing here, right? Do we agree that this is a super important thing to consider? Right? So this basically defines, let me just do this quantity. This quantity is what's called the bias. Yeah. No. 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 Any number of them, as you can work out from just even examples in it. Yeah. Good. Yeah. Other questions? Yeah, phi invert hat is the estimator. This is the expected value of phi hat, sorry, which I should have defined, right? Thanks, Saikat. So the expected value of this quantity is basically just the integral over basically whatever it is that you're measuring, right? The probability of basically the quantity that you're measuring given phi, right? Times phi. Right? And so this object basically just tells you what you should get, basically. Yeah. Okay. This is all okay. How do you know the bound of the parameters, right? He's asking. So this is all stuff that you do before you ever show up in the lab, right? this is a super important question. It's actually super non-trivial, right? Actually, it's straightforward, but it gets lost in the weeds, right? So the point is, suppose I want you to measure, right? I give you a piece of copper wire and I need you to measure its thickness, right? You know it's not a meter, right? So more or less common sense will get you where the order of magnitude of that number is, right? And all of the kind of metrology estimation theory that is done is basically that last mile. Right? This is something I was going to say at some point at the end of this lecture, but yeah, right? So almost all, not all, but almost all metrology that you're doing is this last mile where you're just trying to shave off the 8th decimal point in the measurement, right? There are some instances where you just have like a plane flying by or an astrophysical object, that's going off, and you need to know everything about it all at once, right? And those are different, right? Yeah, please. Probability distribution. Yeah. 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 I know. Yeah, but the ensemble is implied here because this object requires statistics to do. Yeah. So you can't do this at the end of 10 measurements. You have to take enough statistics. Yeah. Okay. No, I'm assuming that I have done enough of them that I can compute either the sum or the integral here. But I will tell you what happens if you do exactly 50 draws. You have to do something completely different, right? Or something related but different. Yeah. Okay. Okay. So let me just. Where is my logo? Okay, that's over there. Okay, so with this, I actually want to begin going down the rabbit hole that will bring us to Cramer-Rao bound in about 15 minutes. So let me consider basically this quantity, which is the mean square error of my estimator. Yeah. I don't know what point this was. This is point number 7. Okay. So I define it basically as the expected value of phi minus phi hat the whole square, right? And I apologize again if this is too basic for some of you. I'm just doing this once so that some of us can just see how it's done, and then I don't bother you with it. Yeah. So I expand out this object. Right. Actually, I don't do that. That would take me longer to solve. What I do is I simply insert right. So remember, it's like any probability distribution calculation that you've done, right? So you have a coin, you toss it, right? And then you calculate basically the probability, the average basically between being heads up and heads down, right? Up and down. Once you've calculated the expected value, there is no amount of expectation that you take over it, right? This is a constant, right? That is the true value of the parameter. It has nothing to do with your statistics. That's the true value. It's in the sky, right? It's the 1 meter ruler that's in the sky. It has nothing to do with anything, right? So these two things completely go away from once you start taking expectation values. You don't touch this, and this is already done. And so with this, what you can establish, and I welcome you to establish this, is that this is I just write the final formula. The expected value of phi hat minus expectation value of phi hat whole squared plus basically the expected value of phi minus whole square, right? So what is this quantity? What I have here is actually just the variance of the estimator, right? So I make 100 measurements and then like I compute my averages, right? And my standard deviation. That standard deviation quantity goes in here. But when I compute the mean square error, that's not all that's coming. And this is the entire point of the story. What's coming is another quantity here, which is the bias squared of phi, right? So this phi minus expected value of phi, what is this? This is the bias, right? I wanted to measure one meter. I got 1.4 meter, right? Whatever, 1.04 meter. That's the bias, right? And so what you have is this equality here, which actually says a lot. Okay. So let me just take 1 second and talk about this quantity, because this is something that at least partly you have seen before, right? So I just want to connect to your own intuition here. So if you take a vernier caliper, right, a screw gauge, it's something that I did in high school or middle school. I don't know if this is still done anymore. Right? Do all of you know what a screw gauge is? Yeah, okay, good. So if you take it was on one of your slides, right, previously. So if you take a screw gauge and what's the first thing you do before you start any measurements? Least count. Okay, excellent. What's the second thing that you do? Zero error. What are you doing? You know the answer is 0. You're asking how much is the instrument reading, right? Does this depend on where you're measuring? Of course it does, right? Because if you take a screw gauge and you untwist it, right? You make it looser. At some point, the threading doesn't hold anymore. Like it just becomes looser and looser, right? At least the ones that I used to play with as a kid, right? Vernier calipers as well. I mean, they're meant to do kind of small measurements. But once you go far enough away from the scale, it starts doing its own crazy thing. So the point here that I just want to drive at is that the bias that you're measuring, not only is it something that you've measured and you know and you handle all the time, you also inherently know that it's a function of the true value that you're trying to measure, right? So I reckon, I don't know this for a fact, I reckon that the screw gauge basically has some bias at 0, right? And then once you correct for that systematics, it starts behaving a little bit better and lower. And then as you go higher and higher, if you're trying to measure like a little piece of cheese with it, right, it's not going to do very well, right? Because it's just not calibrated to go up that, towards the end of its instrumental size, right? So anyway, this quantity is a function of phi, and I want to explain to you what that sentence means. Okay. Now, is this a good estimator? Because what happens, right? If I have this guy, I don't know what the unknown phase is, right? So this is a function of not just the data that I've fed it, which produces the variance, but it also has something else sitting in it, which is the deviation from the true value, which I don't know what to do with, right? So you have to get rid of this. There's no guarantee that you can, right? So this essentially motivates, and I believe I've just speed walked all the way to like chapter 3 of Stephen K's book. This essentially motivates right? Unbiased means B is 0. And you can just stop worrying about it. Yeah? And you need that. Otherwise, the situation gets complicated, right? So I just want to say, this is not the last word on even this chapter of classical estimation theory. If you look in Stephen K, he actually tells you where biased estimators are useful. I will also make this remark at some point when we derive some version of Fisher information, right? Either today or tomorrow. Okay. So these have an acronym. If you want to look in Stephen K, and I'm not going to talk about them more than that. Essentially, all I wanted here was to basically make the case to you that you should allow me to think about bias, right, of an estimator. This is something that is good for us to think about, and it's a thing that we have to handle. It has a role to play in the quantity that we're trying to estimate, right? And to motivate unbiased estimators as a whole, because all of the results that Carl showed you today morning, so on and so forth, the Cramer-Rao bound, so on and so forth, are all about unbiased estimators. What happens when you have unbiased estimators, right? I'll write an equation which has the bias in it and the Fisher information in it, if I get to it today, but okay. Okay, so with that.
I have one question.
Yeah.
Why is it called unbiased again?
I want to set this to 0.
You want to, as in?
I propose that there exists an estimator which does this.
Oh, okay.
And you have to now verify it post fact. Okay. Okay, so now let me just let me derive something to you. It sounds a bit abstract, but oh yes, okay. So given the fact that we've now basically we've now proposed minimum value uncertainty estimates, right? Unbiased estimate. The question is, how do I get to these MVUEs? Like, how do I construct these objects, right? This is the question that you just asked, right? It set me up perfectly, right? The answer is, there are several strategies. You really, so, and one of the strategies is to try and actually just minimize the variance of the estimator, right? And then try and hit an estimator which basically satisfies this along with the bias being 0, right? So you can try and find out whether you can find minimize this quantity and at the same time make it unbiased. Yeah. Yeah. Yeah, there was a question over here, sorry. Yeah, you're just doing different measurements in different parts. Yeah, sure. Yeah, I think people do this routinely, yeah. But you just treat them as separate problems. Sorry, should they? Everything here is basically just the pure statistics that's coming up. Is what you call systematics what is here? I don't know actually. That's a good question. I haven't mapped it on yet. Right? Fair. Actually, I'm going. This is. I mean, this is like 15 years of stuff. So yes. So the point is, there are two things here. One is you have to prove in instances that you do, and actually Carl's one of the people who proved it. You have to prove that if you are constructing basically an MVUE, right, that you can actually achieve it, right? And once you construct an MVUE, you can check that it's unbiased by actually checking this asymptotic unbiasedness. You can just see. So all I'm saying is that if the bias is there, the bias is a 1 over n, so that it just goes to 0 if you take enough measurements, right? So several of the homework examples that I have are exactly this. Right? So if you take a sample if you take n instances of a random variable, right, and you're trying to compute basically the sample variance, right? So when you compute the sample variance, do you divide by n or n minus 1? One of them is asymptotically unbiased, but the other one has a constant bias. Sorry, both are asymptotically unbiased. One of them is just unbiased, which means if you do 10 of them divided by n minus 1, right? So when you do sigma squared divided by n minus 1, this thing is just unbiased. Whereas if you do divided by n, it's only asymptotically unbiased because the numerator picks up an n minus 1. Right? So, yeah. So you can check, sorry, so maybe the answer that you're looking for, you can check by just doing the asymptotics on it. Let's say, see what happens when you take n to infinity, yeah? And whether there is some constant bias at like, okay. Where was I? Okay, good. So, so what I'm going to do is basically try and solve one of these varieties of problems, which will bring us to the story that of the Cramer-Rao bound, which is, my mic is doing something for me, which is basically, okay, good. So, yeah. So one way that I can try and solve this problem is to just simply find the lower bound of the variance of this, and then try and construct an estimator that hits it, and then check that it's unbiased, right? You do both of these, and so this motivates basically the minimum variance of an estimator, right? So in this context, let me present using matrix inequalities here. So let me consider two functions. So I'm doing this for scalars just because it's simpler. You can do this fully for matrix, so a vector of estimators that are trying to estimate a vector of quantities. And it just, there are some matrices that show up that you can just handle, it's not a problem. And if you want to look at the matrix version of it, it's in any one of those reviews. And what I want to consider basically right, A is some constant, and I'll pick this constant judiciously in about 5 minutes. Yeah. So allow me to consider some quantity, some function f, which depends on some variable x, over which I'm going to basically draw a probability distribution and estimate and average. Some g, likewise a parameterized probability distribution parameterized by phi over x, right? And now what I'm going to do is consider some constant a. And if I just square this quantity, explicitly positive object, so the expected value of this is clearly positive, right? Now, if you break it, you can break it into this inequality. right? Where I've just omitted all of the x comma phi dependencies just for simplicity. So all I've done here is just expanded this out, rearranged, and you can just see there's an a and an a square, right? Nothing spectacular, right? On the same page, yeah. And now I make a judicious choice. Let me call this object capital T, and let me call this object capital G, right? And what this basically means now is the expected value of f squared, right? Let me just finish this analysis here if I can. Is greater than or equal to 2a t square minus a squared g, right? I'm just copying from what I have. And now I choose a to be t times g inverse, right? I want to make two remarks here. Remark number one, t and g are both expected values, expectation values, which means there's nothing more to do, right? They're constants. So I haven't broken my initial promise, my initial assumption that a is a constant. It's constant with respect to the probability distribution. And b, I want to make the point that g inverse might not always exist, right? I've basically set down a g inverse, and especially, well, for scalars and also for matrices, you can have an uninvertible matrix or you can run into a zero. Typically, the physics interpretation of this is that you really have a bad estimate. Suppose you put light through a interferometer and you only count what you're trying to measure as the total number of photons that are coming out on the other side. Just the total number, right? And it's not a lossy interferometer or anything. Well, number is conserved. So you learn nothing about whatever it is that you wanted to learn. The total number just being spit out is just one piece of fact that you know, right? So you could estimate really bad things. And so for that reason, this object can basically exhibit nonsense results, which basically you have to go back and interpret as basically your estimator having done something funny. Okay, but with that, blah, 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 what you get is this minimum bound for the expectation value of f squared. And this is basically t g inverse e. Okay, I have to now move. Now, if I choose, now I restore basically its dependence, basically. Right? And so now I bump this to this. You get basically that the variance of is greater than or equal to PG T inverse. Right? If I just close my eyes for a second and pretend that this is a vector quantity, so I'm measuring several things at once, then these are all matrices. And this is actually the famous Cramer-Rao lower bound. Yeah. Okay, let me just quickly do a time check. Okay. So let's choose right? And so this demands there is some demands here, which I will just leave out. There is some demand on the probability distribution that I will just leave out. I'll just write what the name is, and I'll tell you what it means. When I talk about the cousin of this, which is the Kullback-Leibler divergence, basically, it becomes very clear that there are demands basically on the first derivative and the second derivative of the probability distribution, because you're essentially trying to compute a curvature like, right? So this is the cleanest way in which I understand this. This, mathematical as it may be, I find less appealing in terms of my understanding, but I just make this point. With this choice, T, which is the expectation value of F with G, basically you can evaluate that this is -1. You just need to do an integration by parts of a scalar log probability distribution object. And what happens is that the variance of phi is basically greater than or equal to G, and this G is basically I write two more formulas, which you will allow me. That's just that formula written out for integrals. But log, derivative of log is 1 over p times p prime, right? So if you do the derivative, you essentially get another famous formula. Right, there's a square there. So these three formulas, I just want to say, you will run into all the time. This, in general, is called the information matrix, but in this particular case, is the Fisher information. Yeah, so these are the quantities that you've been staring at since today morning, if not before, which is that what was the task at hand? The task at hand is I want to estimate something, and I don't know how to estimate it. I propose that there should be a map between the measurements that I do and the parameter space in which I want to settle this parameter, unknown parameter, right? I construct the mean square error, and I notice that there is a bias which depends on the unknown parameter that I don't know what to do with. I propose minimum variance unbiased estimators, which gets rid of the bias, and then I have to deal with it offline. But having gotten rid of the bias for a second now, I just take the variance and I ask how big or small can this quantity be? And that's just basically bounded by something. Yeah? So that something is an important quantity for us to carry around. Okay. So this is basically one introduction to this. Let me, yeah. Because we are going to calculate this. So the ultimate motivation for us in this workshop is that I'm going to relate P of x comma phi with an actual quantum mechanical measurement. So P of x comma phi is going to be some density matrix which is carrying some phase information phi, right? Times the trace of some measurement operator which is going to carry the outcome index x. Yeah? And now, once I have made these choices, I want to ask the following question. What is the best state to send into my interferometer? Right? What's the best Hamiltonian to use if I could use in a family of Hamiltonians anything that I wanted, right? What is the best measurement to do? All these things depend on the best state is stuck in the initial state rho. The best evolution is how rho 0 gets mapped to rho phi. And the best measurement is whatever pi x is. These are the choices you have to make. And you have to first ask questions like, which choice determines, right, what part of the error budget, right? And so, so let me just say one quick thing, sorry. Let me just say one quick thing, which is that once I have embedded my unknown phase onto a quantum state, all that I can do is mess up collecting this information, right? I can do a very bad job of collecting the information. So the kind of super important thing here is to make sure that your initial state, given fixed Hamiltonian resources, typically that's what exists, right? If you have, let's say, a phase plate, you can't pick the Hamiltonian, it's number operator, right? So it's just the number operator. It's polarization degrees of freedom, some sigma z, right? This is picked for you already. So once this is picked for you, your optimization program as a person who's designing a quantum sensor is to pick the initial state very carefully. And once you've embedded that parameter onto the quantum state, you now have sitting with you rho of phi, and now you need to figure out what's the best way to extract it. And the first step is to figure out how well you could have possibly mathematically done, right? And the second step, it will turn out, I just preview for you, that this is not always convenient, right? So there are all kinds of caveats attached to this. Yeah, sorry.
So I just want to know what is that t is equal to in the
-1.
-1. Why is that?
You just evaluate this. You just you have delta log px comma x phi divided by delta phi is g, and then you've chosen f to be like something. F is the estimator that you're choosing, phi minus expectation phi, and you just need to do one partial derivative, and you'll get there.
Also, shouldn't there be t instead of t square? Expectation value of f square is greater than or equal to 280.
Oh, it's possible. It's possible that I messed up a sign. It's possible, yeah. Ah, okay. Arun, tell me which one is this wrong? Okay, there we go. Fixed. Yes. Yes. So he said, yes. No, it's a particular solution. You can pick whatever you want. And it's just that if you pick, so at this level, this is like doing Cauchy-Schwarz. It's just a matrix inequality. It doesn't tell you too much more than that, right? Then the whole point is basically to get in 4 lines between a matrix inequality, which everyone trusts, and the Cramer-Rao bound, which everyone trusts. That's all, right? So I'm making a judicious choice of G, right? And then now the question is, what is this G? Where did I motivate it from? And I'm motivating. I'm going to say more about it. Yeah, this. Yeah, go ahead. Sorry. Yes, I can say it for an uncomplicated situation, which perhaps helps even more. So I just use this little corner here. So all I was saying was, I basically, let's say I want to project onto some state X, right? Let me actually write it this way. Right? So what I'm doing here is I have an initial state rho naught. There is some Hamiltonian G, right, using which there is a parameter evolution, which I've just written like this, unitary evolution. At the end of the day, I'm asking where is it on the real line, for instance, right? So I put down basically a mask and I ask, where is it on the real line? Is it at a value X that I care to look at? And this quantity basically is a probability distribution, right? Now, what is it a probability distribution of? It's of course dependent on where you're looking, but it's also dependent on the unknown phase. And so in answering the motivation question, what I was saying was, I'm constructing these kinds of inequalities to begin with, because at the end of the day, sitting inside them, hiding inside them, are the experimental quantities I care about, which is choices of initial states, perhaps choices of Hamiltonians, even though this is typically not, so there is something here which I think Anil will talk about, like, you can choose nonlinear Hamilton and so on and so forth. right? Multi-queries and so on. And then what measurement to perform. I proposed just as kind of a way of conversation that we should pick the position measurement, but maybe that's not a good idea. Maybe you want to pick the momentum to look at, right? And so these are all choices available to you as an experimentalist, right? And so to start making rational choices about those in a lab, for instance, I need to know how to connect these choices to the abstract theory underneath. How well could I do? That's what that quantity is. How do I connect it to the lab? That's what I just said, yeah. Yeah, yeah. There are more things that go into it, but yes, you're right. So remember Carl's example today morning. So there was basically, if you have a Hamiltonian, what you do is you put it in a superposition of the largest and the lowest eigenvalues, right? So this choice of Hamiltonian must be available to you. If you can't put the quantum state in the initial superposition of those two, then you can't do it, right? And then you have to have basically what he did in his lecture, if you remember, was he fixed the individual Hamiltonian interaction. Typically, this is what happens, right? Because typically this is conceding that it's an unknown parameter you're trying to estimate. It's a plane that you're trying to shoot. It's a gravitational wave you're trying to detect. There's very little in the way of your control on how the phase gets embedded onto the physical system that you, right? But you could choose the physical system differently, right? So this goes back to bar detectors versus cold atom traps or whatever. So on. All these physical choices affect basically what the underlying physical system is, right? And these are all the kinds of choices that we can talk about now that we have this formalism built in. Yeah. Okay, good. Let me just check very quickly. I have 13 minutes. Oh my. Okay. So what I will do is two quick things, and then I stop at the classical stuff today, and then I continue with the quantum stuff. Well, I was actually hoping to get through half of the quantum stuff today. So, okay. But as I said, I'm happy to not go at the pace that we go at. So what I want to do is put down two more pieces of intuition that I think are very powerful, that have helped me quite a lot, that are parcours for the way these things are thought about. And I think that's about as much time as I'll have today. Okay. I guess this is 9. So this, how many of you know about Kullback-Leibler divergences? Excellent. Okay. So I have some discrete index I, and it's the bin in which my data comes and sits down, right? And I have some probability distribution that I'm going to draw, or you can imagine histograms, whatever you want to be, right? Now, what I want to do is I have a model, right? So so there are two quantities that I can calculate. Let me calculate both of them. It just takes a second to do it. The first quantity I want to ask myself is, how much am I surprised by this data on average, right? I can ask this question, right? Now, how do I answer this question? What does surprise mean? Surprise is whatever the opposite of predictability is, right? So if I just keep seeing zeros, so let's say this is binary outcome, it's not the way I've drawn it, but let's say it's binary outcome for a second. If I just keep seeing zeros, right? After a while, I'm settled and I expect 0, the next outcome to be 0. If it's 1, I'm very heavily surprised, right? So if a probability of outcome pi is very large, I'm not surprised by seeing it, right? I'm not surprised if this is large, then I'm not surprised by the outcome I, by seeing the outcome I in my string, right? So in exactly the same vein, I can write 1 over pi actually is my notion of surprise. Right? Everyone happy with this? Because if p is very close to 0, if I expect this event to be very rare and I see it, I'm very heavily surprised by it. So I want to measure that out by doing 1 over pi, right? Now there is another thing I want out of all of this kind of physics, which is if I have 2 independent copies of this experiment running, I just want the surprise to double. I demand additivity, right? Something we do all the time in thermodynamics. So instead of 1 over pi, what I propose is log 1 over pi, because if I have 2 independent distributions, pi and qj, then it just separates out, right? I remove this for now, but this is the reason why log 1 over pi is a notion of surprise, which also has additivity built into it for product distributions, right? For distributions whose joint distribution is the same as the product of the marginal distributions. And now I simply average over the probability distribution. That quantity is the Shannon entropy, right? Have all of you seen this? If you haven't, I welcome you to look at it. This is basically what is called the Shannon entropy of a probability distribution P. Why have I introduced this? Because I want to ask a different question. This question has a lot of relevance in thermodynamics, in quantum computing, so on and so forth. Not interesting for us. Its cousin is very interesting to us. Its cousin is, I have a model for what I think my parameter is. Right? I have a model for the physical system. It's a beam splitter, it's a laser pointer, it's something. And so I know I can calculate, parallax, blah, blah, blah. I can calculate what I expect to be on the wall, right? So I have an expected probability distribution, which let me just draw in an exaggerated fashion to be very different, right? And now I have a distribution which I see P, and I expect a probability distribution Q. And now I want to ask, what is my average relative surprise? I'm not surprised by those pieces of events where my expectation lines up with the data. That doesn't tell me much, right? So this is already something well known in experimental sciences, right? The thing that you're most surprised by are the pieces of are the events that you didn't expect, that your model doesn't predict, right? And if there is a big gap between what your model predicts and what you end up detecting, there is science, right? There's something interesting there to see. So what I want to do is repeat this exact same conversation, right? For brevity, let me say that maybe I look at pi over qi, right? Because what it does is if pi equals qi for an event I, then p over q is 1 and log 1 is 0. And it just shuts down that event. It just says, I don't care about this one, right? So if I put a log in front, this quantity is a good measure of the surprise of the event I, but the relative surprise of the event I, P versus Q, right? And now I average over the probability distribution P. This quantity is called the Kullback-Leibler divergence between 2 probability distributions P and Q. And that's the way I choose to write it, yeah? The Kullback-Leibler divergence is one of the many measures of basically the distance between probability distributions. It's not quite a distance. And I don't want to rush this conversation, so I'll probably stop just now and take questions for 5 more minutes. But what I will do starting tomorrow's lecture, what I'll do is basically start here, point out to you what the difference between this and probability distances between probability distributions are, and show you that the curvature of this object is in fact related to the Fisher information that we just derived, but in the space of the parameters that we're interested in, right? So if I want to be surprised by a parameter change, theta phi going to phi plus d phi, right? My beam splitter moves a little bit, and I want to be, or the transmission coefficient changes by a little bit. My laser pointer tilts by a little bit. I want to be super surprised by it. I want to measure it very, very accurately. What do I want? I want the two probability distributions to be as far apart as possible, right? So if we start with a notion of distances in probability space and the underlying space being embedded by the parameter itself, right? Then within 2 minutes, we arrive back at Fisher information. And so that's, I think, a good place for me to stop. Yeah, so thank you very much. I'm happy to take questions and so on and so forth. Oops, yeah, I think so. I think so. Let me just check. Yeah. Sorry, there was another question here.
Hello. Q is the expected probability distribution.
Yes, this is okay. This is a good question. So this is what I will talk to you about tomorrow. So P and Q are not symmetric in this particular situation. So P is the probability distribution that you're averaging over, and hence that's basically like the thing that you expect. And Q is the thing that you're measuring, right? If you flip it around, you get completely different results. Mathematically speaking, the Kullback-Leibler divergence is not symmetric. You can construct a symmetrized Kullback-Leibler divergence. It has its uses, including in parameter estimation theory, but story for another time. Yeah, sorry, yeah, continue. When I'm writing a KL of P and Q, I just mean the full probability distributions of vectors on top. Yeah, yeah. So these are, if you want to think of them like that. Yeah. Yeah. No, you're not checking against uniformity. You're simply checking against your own expectation, right? So uniform distribution is 1 over D. If I have a D-dimensional probability distribution, right? It's 1 over D, and that's not what I'm checking against. I'm checking against an expectation that I have, right? Yeah. So let me say the tricky bit here, which is that this is, again, this is the question of what all of this is about, right? If we are discussing precision metrology, right? Precision metrology is not about measuring the first significant digit, right? It's about measuring the last one, right? So there is a lot of prep that is done basically to get rid of all of the other parts of the unknown parameter, where you're only looking at one kind of final digit there. And this is very relevant mathematically. There is a whole theory about whether you're guessing the parameter a priori with zero knowledge in the full set of parameter space, or if you're locally tracking changes of a parameter, right? And these two things are very different objects. I just want to just clarify that. Yeah. So this notion of relative surprise has a huge role to play when I'm sitting at theta equals 0 and it shifts a little, right? That's the way that I think about it. Yeah. In fact, all of the formulas I'll show you will have like a d theta squared, which tells you the variation. You're drawing from a random distribution, but you could have you could actually add a bias to it. So that number doesn't have to go to 0. Right? Just think of screw gauge or whatever, right? If you just, I just give you a scale which is always measuring 1.1 meters instead of 1 meter. Right? Everything else is random, right? Noise, blah, blah, blah. But you have a systematic error attached to the whole thing. And that systematic error doesn't have to be independent of the parameter value that you're measuring. Yeah. Yeah.
This F and G have same role as P and Q here, right?
No, I'm just using that to prove a theorem.
Okay.
No. Yeah, I'm just, so, if you look at Cauchy-Schwarz inequality derivations, right? You start with 2 vectors and then you construct some blah, blah, blah quadratic inequalities. And then you start, like, that's exactly what I'm doing there. It's nothing more than that. Right? Nothing profound here. Okay.
I mean, I don't understand this implication of Cramer-Rao lower bound.
The rest of the week.
Okay.
Yeah.
Yeah, just one thing. So this derivation you did, but for an experimentalist point of view.
Yeah.
So if I'm trying to construct the estimator to saturate this bound, there's no recipe for that. No?
There is a recipe for it, actually, due to Carl. There is a recipe for it for single parameter, but I think multiple parameter, there is
The
no.
Cramer-Rao bound doesn't give a, it tells you how
Cramer-Rao
badly
bound
I'm doing
tells
or
you,
how well I'm doing.
And what it is that there is this thing called the symmetric logarithmic derivative, which I will show, in the next thing. And the SLD actually is a POVM that you can implement, and that POVM will get you where you want to go, right? So this is now, I have made the God's honest truth comment, which is on the wall. Let me tell you the practical comment here, which is most SLDs are unimplementable. If you just say to an experiment, please implement the following POVM, you write it in a paper and give it, they just don't, it will be too complicated, right? So basically, a lot of the research in parameter estimation for mid 2000s to like now, part of the conversation is how do you move to basically experimentally viable measurements and construct estimators which get you as close to basically these theoretical bounds as possible, but are still basically implementable, right? So what's the game there? So in fact, I have a diagram in one of the other lectures that I prepared, which is, if you think of the line of, where variances are, there is the theoretical bound which sits somewhere. There is basically the achievable bound, which for single parameters is 0, right? I mean, there's no gap there. The achievable bound is a theoretical bound. But for multi-parameters, there is a gap there in general. And then there is the practical bound, which is actually even farther away. And so there is this distance covering is a whole thing, basically.
And just another quick thing, that the way you hinted at the KL divergence connection to Fisher information and even the diagram you drew,
Yeah.
it seems like this will work for a biased estimator also, right? Like, or this definition holds, or?
Yeah, I haven't done the bias estimator calculation this way, but I think what will happen, I can show you the actual bounds I have. So the bias of the estimator appears in the numerator. In principle, it spoils the story because the variance basically, which essentially should just come as 1 over the Fisher information here. So 1 over G, sorry. Basically, what happens is that this this quantity basically has a 1 plus okay. 1 plus the parametric derivative of the bias squared, whole squared. This is what is on the, so wait, yes. And how do I remember it? Because you can construct biased estimators which actually lower the variance. So you shouldn't throw out biased estimators per se, but they're messier to deal with. If their parametric derivative, so their derivative with respect to the unknown parameter is negative, then actually that 1 plus can do some stuff. Now you have to check what's happening overall. This is how I remember it. Yeah. Okay. More questions? Okay. Thank you. Thank you, everyone.